Hello everyone. You are probably wondering who I am, and that has a simple answer. I am the father of trigonometry, not Hipparchus, but the triangle, a trigon more specifically. From me came my 6 children that you all know well. Sine, cosine, tangent, cosecant, secant, and cotangent. The 6 trigonometric functions. Now everyone knows the graph of these functions, clearly shown here. Their meanings are quite simple, all revolving around one key point. As x changes, the measure of the angle in a unit circle changes with it. So my x-axis for this video will be represented using units of pi to fit with the radian measurements. So that's pretty normal and all, but there is one minor problem with the trigonometric functions. Combining them. Have you ever wondered what the sine of the cosine of x is? No, that's to be expected. However, I want to show you all this monstrosity. Yep, that's right. This is an abomination of a graph. And yes, it either looks like this or is unable to be graphed at all. Today, I am determined to explain why this graph looks like this using the basic properties of the 6 graphs. So, let's begin. What are we even looking at here? Well, this is the cotangent of the secant of the cosecant of the tangent of the cosine of the sine of x. In order to work through this, we need to start at the root of the problem, sine of x. This is simple enough. Everyone knows the standard sine graph, however, things pick up when we reach the cosine of the sine of x. Every value passes through a sine check prior to entering cosine's function. All values of sine of x will come out between -1 at 3 pi over 2 and 1 at pi over 2. However, when taking the cosine of these values, the period shrinks from 2 pi to just 1 pi. This happens because the new limits of -1 to 1 confines the new graph to the first and fourth quadrants, both of which are positive for cosine. Both -1 and 1 result in the smallest output of approximately 0.54, occurring periodically at a rate of n pi plus pi over 2. The upper limit then happens at n pi, being a value of 1. So that wasn't too hard now, was it? Well, the others follow the same format of the output of 1 being the input for the next. Tangent's new limit is approximately 0.54 to 1. This has almost no drastic change, surprisingly, with the outputs falling just under 0.6 and approximately 1.55, corresponding to cosine of x's period very cleanly. Unfortunately, the simplicity disappears as soon as the black sheep trio of the trigonometric functions cosecant, secant, and cotangent get introduced. Cosecant doesn't quite break it yet, but the curve seems clearly odd, flattening out close to n pi. This is the end of normality, though, with the final comfortable limits being between almost 1 actually being this, and approximately 1.77. Now, we reach the point where I can't explain every detail due to some calculation limitations. But the secant of the cosecant of the tangent of the cosine of the sine of x finally ends up resembling a secant graph. The lower limit of the upper asymptotic curves is approximately 1.85, while the upper limit of the lower asymptotic curves is approximately -5.01. It has two unique properties compared to a normal secant graph, being centered around its asymmetry. Its asymptotes vary in separation, being either approximately 2.38 units apart or approximately 0.76 units apart. The top curves are wide while the bottom curves are thin, adding to the asymmetry. However, this graph is nothing compared to what comes next. Tossing cotangent into the mix is the perfect catalyst to break math. There are 4 key components to the graph. First, we have the lower curves. Just like the upper curves of the graph before it, they are the wider curve, having their limit at n pi. Then the upper curves are like the lower curves, being the thinner curve at n pi plus pi over 2. However, the difference is in how both curves were confined further and were flipped as to which was on top. However, those curves need no explanation. They are the normal parts of the graph. What is unique is the several cotangent curves approaching pi over 2 and tangent curves approaching pi. What is interesting is that their confining limits get progressively smaller as we approach the asymptotes of the previous graph. Each curve is thinner than the previous as you get closer. We then enter the most interesting region, the void, named for the fact that it just becomes an abyss of a line. So, what is happening here? Well, it's actually the same as the previous feature. The void is an area where the asymptotes become so tight that the curves become nearly indistinguishable. There are infinite curves jammed into the space caused by the former graph's approach to infinity. As the values increase, the period of the curve shrank more and more, confining them into this infinite void. Now that is cool and all, but there is one minor problem. There are several other ways to arrange the 6 functions. For obvious reasons, we will not be covering them.